Okay, so we'll be looking at the topic hash functions. So first of all, the question comes to our mind is that what is the hash function, right? Uh, Typically, a hash function is a mathematical function that takes uh, input which is of arbitrary size and produces an output that is of a fixed size. Okay, so as we can see here in the terms of computers, we take the message as an input which can be of any length and pass it through a function, that is the function is represented by h, and it produces a hash value that will be certainly a fixed length value. uh, I mean that's the property of a hash function. It will definitely output a fixed length value, whatever be the size of the message. So we can look at the properties of a hash function. That will be, there are typically a lot of properties, but I have listed only the four of them, which will be uniformity, efficiency, deterministic, and universality. So let's look at them one by one. First of all, we have uniformity, right? Uh, Uniformity generally means uh, that the function, uh, that the domain of the function is such that the range that is being generated by all the input values when they are being passed to the function is uniformly distributed in the what do you say, in the length, you know. So if a function has a domain of, like, we can say 1 to 10, and it produces the range of, for example, a to z, then the distribution of all the hash values from their message should be uniformly distributed among all the values in the range, right? Then we come to the efficiency. So the way the hash values are stored, which are generally or typically the key value pair model, not like we used to store previously in the linked list model. The hash values are really efficient to store. Like we can have a lot of very large amount of hashes in a single database, and that can be passed, stored, and accessed very easily without any problem. And also one of the thing is that it is efficient in that manner that it cannot be updated very easily in the database. So the determinism of a hash function comes from the sense that for any given input, the value of the function must always generate the same hash, or there won't be any point if the hash function is not generating the same hash for the given input every time it is being passed to the function. The last one comes as the universality, and that means that the hashing function is chosen such that it is really random. It is just like choosing a random function which will generate the hash for us for the given set of inputs or the message in this case. After this, we are moving on to the cryptographic hash functions. So the cryptographic hash function is nothing but the mathematical form of the hash function. That's all. When the hash function takes its mathematical form, I mean, we have the domain, we have the range, and a function which can be clearly defined using mathematics, it becomes a cryptographic hash function. So the cryptographic hash function, or CHF, has the message which is being passed as an input, which outputs the value that is called message digest or the hash. So to keep in mind, it is always a one-way function which cannot be reversed. So if you try to somehow reverse engineer the hash value, it will be impossible to do that. I mean I cannot even say it will be infeasible. It will definitely be impossible to do that. The only way to find the message will be to use the brute force method, very typical method which was used in the previous days to crack the hash functions. I mean the computers with really heavy computational power, they can be used to brute force the hash values for certain hash functions, I believe, in the past. Not for the for the new ones. For example, SHA 256. These functions cannot be brute forced even now, as far as I'm clear. Please let me know if I'm wrong. So let's move forward to the properties of these CHF. So the properties, there are generally three properties for any CHF, and that will be pre-image resistance, the second pre-image resistance, and the collision resistance. So these three are the only properties that we'll be discussing today. The pre-image resistance says that it should be computationally impossible to find the reverse of a hash value using the hash function that we have. So what it says that even if we have the knowledge of the hash function that is being used, and we have the final hash value, it should be computationally impossible, or the function should be irreversible if we are saying in the mathematical terms. So yeah, as you can see in these lines, it is clearly mentioned that if we have a function h that produces a value z, then it should be a very difficult process, or it should be impossible to find the value z using the input x. Sorry, it should be impossible to find the value x using the value z. So this property, it protects against the attackers who try to find the input using the hash value. The irreversibility of the hash function. Basically, it proves that. So after this, we go to the second pre-image resistance, which generally means that for any given input, there should never be another input that produces the same hash value. So if we have an input x and we have an input y, there should not be any input, whether x for x not equal to y, that it produces the same hash value z, right? So here we can see that for the function h of x, there should never be two inputs x and y that they are equal, that the hash value for them are equal. So, and this is called the second pre-image resistance. The third property is called collision resistance. This means that it should be very hard to find two different inputs of variable length which results in the same hash. So it is almost similar to the second pre-image resistance, but it is somewhat different in the sense that the input should never be the same, right? And in the second pre-image resistance, we were saying this in the different terms. For example, for what we were saying there was that if the hash for the value for the input x produces h of x, and the hash for the value y is h of y, then they should not be equal. Here we are saying for any for any hash value, there should not be two different inputs. So the way of saying is different, but the meaning is somewhat same, or that's what I am comprehending. So and that is how you can see it is also written here that if a function is collision resistance, then it is by default the second pre-image resistance, just because they mean the same, almost the same. So yeah, these three were the properties for the CHF. Now let's see how a hashing algorithm is designed, right? So fundamentally what happens is that there is a mathematical function which takes various blocks of data. It calculates, it does some operation on that, produces a hash value, takes another data block, produces the hash value, and goes on until it finds the end of the message block or the data block. So this is how typically a hashing algorithm, in a very crude way, how a hashing algorithm is designed. So we can see in this image how these things work that I just said line by line. So what we have is we have a seed value and the blocks and the division blocks for the message. So we have n blocks, and for every block we just go on passing that block to the hash function that produces the hash value, and we keep on doing that until we find the very last block. And after that, the summed value is what we get as the hash value. So the hash value keeps updating in every block that we pass through the hash function, right? So uh, I think that's all for the hash function. Thank you for watching.